and we get data for this problem through the GLDB2 dataset. And due to its size and crowdsourced nature, a lot of the quality of the photos and balance of the classes are degraded. Next slide, please.
Data processing. Next slide, please. So here's our overall framework for data processing. I'll go through each of these steps in the next few slides. Next slide, please. So we start with dataset scoping. So we originally have over 5 million images from 203,000 different classes or landmarks in our case. And what we first did was we basically took one frame of these classes. So if you look at the image on the bottom right, we tried to ensure that all the images from all these classes were relatively balanced as well. Then we further brought it down to 26 classes just to reduce the size of the dataset. Next slide, please. So a lot of the images within these classes were kind of irrelevant to the class itself because the dataset itself was kind of crowdsourced. So to kind of remove these images, we used the Delph network. So it has 3 basic steps. So first we would extract the features from the images, then we would match them to get their inliers and assess it with a threshold. So if we look at the image on the bottom right, if we look at the window on the right, it basically matches very poorly with all the other images in its class. So what we do is we discard that image. Next slide, please. So for balancing, we basically take the median of the total images for all the classes. And whenever a given class is above that median, we shave off the top to reach that median. And whenever it's below, we augment to reach that median. Next slide, please. So for finalizing our input, we take what we have with web scraped images and we resize these images and we merge them together. Then we resize images, normalize them, and pass them into the network. Some limitations is that Delph could be very resource intensive and a lot of human input was required when manually basically bringing down the classes to 26. Next slide, please.
So now we talk about models. Next slide, please. Starting with our baseline of LENet, which we trained from scratch, we then went on to transfer learning with VGG16 and ResNet34, while only changing the fully connected layers. Next slide, please. The model we ultimately ended up with and focused on was ResNext 101, which is a variant of ResNet that is 101 column layers deep and has a special implementation feature of cardinality, or just 32 parallel paths for each block or set of 3 column layers, unlike normal ResNet that just has one sequential path. Next slide, please.
To increase test accuracy and reduce overfitting at the same time, we decided to add an extra fully connected layer to the final fully connected layer of that ResNet 101. We added a dropout as well to reduce overfitting slightly. Another notable change was how we reduced from the 1,000 ImageNet classes that the model was trained on to 26 classes from our own dataset. Next slide, please. Now we'll be talking about our results. Next slide, please. The primary metric that we chose was top 1 validation and test accuracy because we were concerned with how the model could generalize to unknown images. We chose not to focus on specific metrics because this was meant to be an informational tool, not a life or death tool. And as a result, we were just concerned more about the success rate rather than a specific metric. As you can see below, here are our best hyperparameters for our models. Next slide, please. In this plot, you can notice how every single transfer learning model is better than the blue LeNet baseline on the bottom. This is a strong proof of concept that transfer learning works for this problem. Furthermore, our best model was the modified ResNext, the purple line, as it achieved a maximum test accuracy of 96%. And you'll be seeing a zoomed in version of this plot later on. Next slide, please. So in this confusion matrix, we plotted it to understand where exactly our model was vulnerable with respect to incorrect classifications. This transitions into the qualitative analysis of our project. Next slide, please. As you can notice, the model struggles in specific commonalities. For example, when it notices a common structure, like trees in 2 completely different landmarks. It also struggles when landmarks look really similar to each other, like the bottom row, where each of the 3 images correspond to a different landmark if they look very similar. A potential solution to this would be to heavily data augment such similar classes to present enough diversity within their training images so that the model doesn't get confused later. Next slide, please.
Discussion and learnings. Next slide, please. So what are some things we learned from our data processing? So looking at the test accuracy plot on the top left, we see that Delph greatly improved the performance of our network. And this is because we're removing unwanted images that don't really match well with any of our classes. In terms of augmentation didn't really help us improve our generalization. And this is it could be mainly because our data was crowdsourced, meaning it came from a lot of different places and it already had that natural level of diversity within it. Next slide, please.
Finally, looking at our total results in the table below, we see that a high number of total parameters typically leads to more test accuracy. However, plotting the data and fitting a near perfect exponential curve to it, we can see that there are significant diminishing returns from adding more parameters to get higher accuracies at higher accuracy domains. And this is also why we use transfer learning and dropout to help us minimize parameters we're actually training and to alleviate the overfitting that exists and observed when adding like significantly more parameters. And we can also see that we do gain marginal benefits in our accuracy graph. And in terms of final remarks, we want to make sure that for the future, we are mindful of irrelevant data that may exist and using augmentation intelligently and appropriately.
So
consider dropout as an effective mechanism for reduced overfitting when you have a lot of parameters.
Yeah, thank you. Yeah, when you hear that sound, just pick a sentence and say it, but don't just keep going. So
I didn't hear a sound. I'm sorry.
oh, is that right?
Yeah.
Oh, okay.
Yes.
I should try to get this thing to come through here. Okay, very interesting. I want to ask a bunch of questions about, well, let me say, having to deal with a 5 million data set and cut it down is a difficult thing. That's what you spend most of this first bit talking about, right? That's what you call data scoping. Is that correct?
Yes, yeah.
And I didn't quite, can you tell me what you meant by Delph filtering? What was going on there?
Yeah, so basically the idea of Delph was whenever you have an image within the classes, a lot of the images were kind of irrelevant to the class. So if you had like a landmark.
What is Delph? Like what? It's a word.
Yeah.
It's an acronym. I have no idea what it means.
So Delph was
I heard
basically
you describe this. I don't want you to repeat what you've already said. I want you to tell me what Delph is.
Okay, yeah. So Delph was basically so it first consisted of like a pipeline to extract the features, and then it would do some geometric variations to get the matching features.
Okay, so
basically,
just to be clear, it's something you found that does processing. Is that right? I have no context. Yes. It's a word I've never heard before, right?
Yes, yeah.
Network that it's a network in and of itself that calculates features in its own representation and stores in a Delph file between two.
Yeah. Images. So again, you're speaking at a really low level of detail. I think the right way to answer this question, just to help you out, is Delph is a piece of software we found that takes this input and produces this output. Don't tell me anything else. Just input pictures, output is what?
Okay.
Well,
so our model altogether, it takes in two images, a query image and the data set of database images, and it produces the number of common inliers between them. For example, the bottom two images, it takes in those two images as input, realizes there's not a lot of common within them, puts out three inliers. There, on the top image, there were two really similar structures, and it produced a lot of inliers.
I actually don't know
inliers are common features.
Sorry, Arsh, can you hear me?
Yeah.
So I have to stop you when you use words that I don't understand, because that means I'm not following what you're talking about, which is your job as students, by the way. So here I am you're the teacher, I'm the student. You use the word inlier, don't know what that means, lost.
Yeah, so basically it would take two images as input. So basically like in that picture on the bottom right, and then it would mark the features with those black circles. And whenever it sees features that match, like it would mark them as inliers, which are the blue lines.
Inliers are basically the common things the network sees between two images, just common features.
That's what an inlier is. Two things common to a picture.
Okay. Yeah.
And is this network trained by you guys, or is this pre-trained on some other data set?
So yeah, it was a pre-trained network on another data set, and it applied really well to our data set. So
okay, thanks.
So do you understand this point about you start using a word and nobody's heard of it before? We don't really have any context. So it's actually super important for presentations. It's the best way to make people be quiet because they don't know what you're talking about. Except my job is to tell you I don't know what you're talking about when you're doing this. So make sure you don't do that in your final report or future presentations. And I think I want you to be careful answering questions. I don't think you've told me what a single label is in this data set. Tell me one label, the name of one label.
It's the ID of the landmark.
Yeah.
For example, if you
is that a label? Idea of the landmark? I just want one
ID.
example.
It's a single classification problem. It's the ID of the landmark.
Are you looking for the name of a landmark?
No, I'm looking for the name of a label in your classifier.
Yeah,
Oh,
so
yeah, like
if you
with
scroll down to the qualitative slide, we basically have the labels for some images in our example. Yeah, just
Qualitative
one.
results. Yeah.
yeah, so the
Yeah.
mountains is
Okay, slow down. We're 103.88899. That's a label? This?
Yeah, that corresponds to a specific landmark.
I thought you said and there's only 26 of these.
Yeah.
Yes.
yeah. So basically, in the total data set, each landmark has an ID identifier, and so we just use the ID identifier to like represent each
So
image.
the answer to my question is the label. You see, the number doesn't mean anything to me. The label, the only label, is the name name of the specific landmark. That was the purpose. I guess I didn't quite pick that up at the very beginning. Okay.
Yeah, but when we're training, the label is obviously not the value of the number itself. It's what how encoded by the data loader.
Yeah. That's why the number is meaningless to me. So,
Yeah.
Yeah.
this, you know what this should have said in this presentation? Predicted the great monastery of Bulgaria.
Yeah.
Actual, the lesser monastery of Bohemia. That would have meant something to me. This meant nothing to me. So,
Yeah, we just want to show more the similarities between the different images.
no, you're not catching my point. So let me try it one more
Yeah,
time.
we
For
understood.
us to understand, just to be aligned with what the goal was, because I kind of forgot the goal. The label would be not 17311. It would be the Great Monastery of Bulgaria. I'm making it up, of course. And this would be something else, or that the lesser monastery of Bohemia, is what got misidentified. That would have been more comprehensive to me. Do you understand?
Yes. Yeah.
I'm talking about what a human needs to understand in a presentation. Part of the goal of this course is about that. Okay. There's more to say. At one point, one of you said, accuracy and all that is meaningless. Only success matters. And I'm paraphrasing, and that makes no sense. Eventually, you did talk about accuracy. It is numerical. When you're talking about quantitative things, it's got to be accuracy or F1 or something. And so, when you said we just need to talk about success, you then have to define your numerical definition of success. Does that make sense?
Yeah, I was the one who said that, and I believe I said that we chose top one validation and test accuracy as our primary metric. We chose not to focus on like further specific metrics like F1 score, for example, because we were concerned about the
F1
success.
is accuracy, right?
Sorry.
Like, I mean, top one is accuracy.
Yes, yeah. That's what we chose. Yeah.
You kind of said we're not going to pick anything, and then you went and said we picked this, and then it's like that was quite confusing when you said that. Your goal as engineers is to quantify success. The previous group, I know Ghostwriter had a whole discussion about how do we know what's right or not, and that is actually a core part of the engineering that has to go on. That's not just about turning the crank. So describing that in a way that is coherent is important. I get the top one is okay, but you took a very meandering path to go there, saying all we want to do is talk about success. So I'm going to run out of time. I'm going to give it over to Phil. Phil, you're the governing TA.
Yeah. Nice job, guys. So one thing I want to say is you typically don't want to excuse your network performance by saying the task isn't life or death. So accuracy isn't that important. And then the other thing about pre-processing, the thing that I was sort of confused about is the different augmentation procedures for images above the median and below the median. So usually when you make these sort of choices, you want to provide some context as to why the processing is different for different brightness of images.
Yeah. Okay.
Maybe you want to, I don't know, provide some context or just expand on it in your final report.
Okay.
I did find this interesting. This balancing slide was you talking about how to balance across a very large balance your classes across all the different images. that wasn't easy to do given the many that you started with. Okay. All right, we should